Hello, everyone. My name is Anjali Sharma Tiwari. I'm currently a junior at Basis Independent Silicon Valley. Today, I will be presenting my project, Predicting Excess Bond Returns Using Neural Networks. So before we dive in, we first need to understand what excess bond returns really are. So let's take a step back and define some terms. First, excess bond returns are the predictions of bonds of different maturity durations. They are predicted using the yield curve of monthly rates and are improved upon using forward rates. The ground truth for all bond prices is the yield curve. From the yield curve, we can compute the market's current estimate of the future yield. So why now? Well, recent advancements in the fields of econometrics, statistics, and computer science have spurred interest in reduction and model selection techniques, as well as predictive models with complex features, such as sparsity and nonlinearity, both in finance and economics. Over the last 2 decades, however, the use of such methods in financial economics literature has mostly been limited to data compression techniques such as principal component and latent factor analysis. So why does it matter and how does my approach differ? Well, neural networks allow for complex nonlinear combinations of forward rates and the 128 macroeconomic factors of the economy. Therefore, the use of machine learning has the potential to improve upon existing work and lead to better predictions, but it does come at a cost. The cost is that there is a lack of visibility into the functioning of the neural network. This is because neural networks make connections between factors, but there's no clear relationship defined. This makes it hard to extract a general equation or make generalizations that can be applied to all bonds. So, some prior work in this field are data compression techniques such as principal component analysis, latent factor, random forests, and regression trees. These have been used since their techniques provide good visibility into what the strongest relationships between inputs are, and some even output generalized equations that can be used across all bond predictions. So my primary input data were the daily and monthly yield curve data points and data about the 128 macroeconomic factors. So the yield curve data. The yield curve data that I used is comprised of zero coupon bond interest rates ranging from June of 1961 to December of 2023. For every month, the data represents the interest rates and bonds issued with maturity durations ranging from 1 month to 30 years. So depending on if a bond was issued for a shorter duration versus a longer duration, a different set of macroeconomic factors play a greater role. For short-term bonds, such as a 2-year maturity, which is what I looked at, factors like consumer confidence in the stock market, labor market, and hourly earnings played a larger role. Of the 128 macroeconomic factors affecting the economy, the most impactful for long-duration bonds, such as the 10-year maturity bond, were civilians unemployed, consumer price index, also known as CPI, and commercial and industrial loans. Bond prices are affected by interest rates, and these interest rates are affected by the expectations that consumers have of the economy's performance. Now, forward rates. What are they? Well, forward rates essentially are the interest rate on a loan or asset that are set to take place in the future, but are priced as of today. Forward rates are calculated using 2 zero-coupon bonds, whose maturity differ by the time period needed for the forward rate. The forward rate formula which I used is a combination of the characteristics for a short-term bond and the characteristics of a long-term bond. The formula is as follows. The rate of a long-term bond raised to the power of the number of periods and is all divided by the rate of the short-term bond raised to the power of the number of periods for that. So in terms of the inputs into the neural network, using just macroeconomic factors or just forward rates only gave a slight improvement when compared to the traditional methods of predictions, such as random forest or regression. But these small improvements are not by any means impactful enough to make a real difference. So with each of these having individual impacts, I decided to combine these two inputs to see what that would lead to. So when I did combine the macroeconomic factors and the forward rates, I saw a big jump in the R squared, and it gave far more accurate predictions than the traditional formula. Even though this was a far more accurate model, it did come at the cost of not knowing exactly to what degree each input impacted the output. So here are my findings. With respect to EXP and REC, these denote whether it is an expansionary or recessionary time period in the economic cycle. So when comparing the PCA, the principal component analysis, and the neural network models of long run, which is a 10-year maturity, and short run, the 2-year maturity bonds, the conclusions were as follows. 1. The model was most confident in periods of recession, and this was likely due to the fact that events leading up to a recession are quite predictable, so the model can easily detect and configure a pattern. 2. The neural network was more accurate than the PCA in every given instance. And 3. The R squared was higher for forward rates with the combination of macroeconomic factors than it was for just using the forward rates alone. Therefore, the use of the neural network with inputs of both the 128 macroeconomic factors and the forward rates had the best performance. So here are my model statistics and how they compare to the current use of forward rates alone. So the nodes per group denotes the number of combinations possible. When using forward rates only, there is only one node, since there is only one input. But when using macroeconomic factors plus forward rates, there are 3 possible node combinations, one for each of them used individually, and one input for them working together. Therefore, the total combinations per retraining, as you can see, is far greater when using both the 128 macroeconomic factors and the forward rates than just using the forward rates alone. In terms of future work, I would like to include more variations, such as adding different layers or node combinations, since this would add more variability and could produce more accurate predictions that better model the real bond market. So some key references that I used throughout my data and my findings were the following. So the first 2 papers introduced the idea of the 128 macroeconomic factors and interest rates, as well as the fact that forward rates are a leading factor in the determination of bond prices. And the last reference is all the yield curve data that I used. Thank you so much for listening, and it was a pleasure to be here.
Anjali, that was awesome. Thank you so much. We have a question in the chat, but I want to ask one question to start us off, which is, like, what was your spark for your interest in this research?
Yes. So I had done prior research using neural networks. So I made object detection models and NLPs. So I did know about the architecture of them, but I also had quite a big interest in the financial sector, and taking economics in school and having my dad work in the financial sector, I was really interested on how are these prices able to be determined when the real price of anything is just subjective. So that's how I came to have this kind of spark and interest for how can I be able to predict what these bonds are, since the current system being used is so rudimentary.
Fascinating. The question in the chat is, can you talk a little bit more about your experience working on deep learning and neural networks?
Yeah, so like I said, I did have some prior experience working with object detection models like YOLO and other computer vision as well as NLP models. So when I was able to create this project and have some sort of idea of how I wanted this project to be facilitated, I was able to contribute that same architecture, and I was able to run this on different platforms such as Kaggle or Google Colab or Jupyter, and I was able to see the differences in how CPU and GPU power was able to really affect the determination of how well or how fast these trainings were able to be done. So yeah, so that kind of experience was able to translate over here as well.